Hello, my name is Yang Nguyen. My partners are Rafael Medina and Juan Martinez. In this project, the problem that we are trying to solve is how to make thermal energy more economical. We have discovered that the world use of energy, only 1% of energy is solar energy. Currently, solar energy is most inefficient, and to get that energy is hard to store, and the production of solar panels is quite expensive. The challenge in this problem is to increase the production efficiently to make solar energy a safe, affordable, and reliable source. Analyzing each step in the solar energy process, we have searched for any small factors that could possibly affect the cost of production. In order to solve this problem, we have made a program that compares all 50 states of the United States usage of energy based on how much they spent and how discovering a new element would produce a solar panels efficiently could vary an increase in solar energy use. In the first section of the code, we have inputted data based on how much energy the states use and how much they spent per kilowatt hour. The data stored was into three variables: raw1, data1, and sheet1. Raw1 consists of all the number values that were available in the Excel file. Data1 consists of all the strings that were in the Excel file, and sheet1 consists of raw1 and data1 combined. As you can see, Sheet 1 has everything, Raw 1 has only the numerical values, and Data only has the name of the states. Since in Raw 1 the second column it's in megawatt hours, but the amount of cents that we're trying to compare it to is based on the usage of kilowatt hours. Because of that, we have to multiply by 1,000 in order for megawatt hours to convert into kilowatt hours. Next, we took the average of kilowatt hours and the average amount of cents for every state into average cost. The next thing that we will do is we would want to make a plot based on the data that we have. We decided to make boundaries for anything that's above or below the average lines of kilowatt hour and the average cost. And since we plotted 4 different plots, we made them all into different colors for specific reasons. We made a legend to determine which states they spend is inefficient, efficient, too expensive, and some that are ripoffs. On normal standards, we would try to use the method polyfit to make our equation for us in order to plot the trend line. But because the points are scattered just like this, you don't really see that much of a trend line. And because of that, we decided to just make a horizontal line and a vertical line based on our average cost and our average kilowatt hour. The average lines divide this graph into 4 parts, as you can see. So I devised to make a function called counter. Counter would count the amount of states in each section of the graph. In the function counter, it is run by a for loop, which is start at the index of 1 and it goes up to the length of kWh, which is 50. For every condition that it passes, if it's true, it will count for 1. For this one, it's the bottom left corner. This one's the top left corner. This one's the top right corner. And this one is the bottom right corner. Every single time that the loop is run, it will add an index of 1. So it will actually go, instead of it being starting at 1 next, it will start at 2. So then kWh will be starting at an index of 2. And it will keep on running until it hits 50. The next part of our code is that we input a new state. How much does it spend per kWh and how much it used in megawatt hours. And then we made a cell array for those 3 inputs, and then we added that into the original data, and we made it into a new Excel sheet called new data. Based on what we input, we can now go to the conditional statements. If what we input for new cost is less than 0, it will give us a warning and it will make it into a positive number. If it equals to 0, then it will print out an error and it will terminate the code. If we input MWH and it's less than 6 million, then it will also print out error, just because the minimum of all the 50 states, it's somewhere near the 6 million, which we don't really want. Now for the rest of the conditions, will be based on where that new point will exist. So if I have an average kWh and an average cost, which if remember before, it was a line like this. So we will have two graphs, right? For every if and else statement it will exist in the certain locations. So for the first one, the average cost is greater than the new cost. At the same time, the average kWh is greater than the new kWh. It will exist anywhere in this point. Now, if the average cost is still greater than the new cost, but the average kWh is less than the new kWh, it will be in this line, in this area. If the average kWh was less than the new kWh, at the same time the average cost is less than the new cost, it will go into this area. And if the new kWh is greater than less than the average kWh, but the cost is still higher than the average cost, then it's over here. Now when we run the code, it will give us the graph, and then we have to type in the name, which I'm just going to put my name, the cost in cents, 6.25, and then I'm just going to put something over 6 million, and it will say that it's inefficient, which is the first else if. Now if we run this again, we put that and something that's really high. It'll say that it's efficient and cheap, which is the second area on the graph. Now let's try this again. Now this time we're going to change the amount of cents, and we're going to keep it as high as before. It's expensive, which is in the top right corner, and now we run it one last time. And then which is a ripoff. And then after we have that plot, now we can open the new data file. And as you can see, the data that we lately input is right here. In the second part of the code, we are dealing with the light spectrum. For us, the light spectrum is like 7 different colors that are visible in light, and apparently each color has a different wavelength and a different frequency. So in our light spectrum Excel sheet, we have different frequencies and different wavelengths, and we have the absorption of energy as well, where it's categorized by a 7x3, one designated for each color. Now as I scroll down the program, you will see that there are 7 different plots: red, orange, yellow, green, blue, purple, indigo, and violet. Each one is a different sign graph. The higher the more it goes down in colors, the higher the frequency. Now as we can see when we run this, the higher the frequency, the higher photon energies are the element's going to absorb. So in this process, If we can find an element that absorbs more light because of the higher frequency, then we can use that element to replace silicon, and it will probably benefit on the development of building solar panels. In the third section of our code, it is somewhat similar to the first section where we input the same Excel sheet and we have the same data, except this time we multiply by 0.01 on kWh and multiply 0.01 on sense1, just because the amount of solar energy that's used in the world is 1%. And we have the same plot as before, except with a different axis. Then we stated that the production percent is 0.005 because that's the equivalent to the percent of solar energy costs implemented on the people. And then we used that factor to determine the solar panel cost and the total panel cost, which is the sum of every panel of solar panel costs. Now we have an input variable called discount. Discount is depending on how our new element will affect the development of solar power panels. So if we input something that's less than 0, it's obviously going to be an error because we'll lose money that way. If we have a discount equal to 0, then that means nothing. And if we have a discount greater than or equal to 100, that's practically mean it's free, which nothing is free. Now, as we go through the rest of the program, the new total percentage is basically 1 minus the discount percentage, and the new panel cost is basically the total panel cost that we calculated earlier times the new panel cost. And then the new power usage is the new panel cost times the solar cost, which we will see later how that affects the data from the original. Now, since we have the plot, we put it based on the new average that we have, and then when we plot it, it should show a trend line that every single point on the graph will be above the average, which is how we're going to save money. So when we see this is the original plot, where some of them are on the bottom and some of them are on the top. Now, when we input a discount, let's say 12, it'll plot a new graph, where every single plot is above the average. Even though this program can be used to determine if we can make thermal energy economical, there are limitations that are existent in this program. If we had a plot that had made a trend line instead of what we had, which is a scatter plot, it would help to have an equation that would vary the production of solar panels. Could have been determined more factors that would benefit economics for thermal energy, and probably have a better precision of than what we could have gotten, which is comparing the points to the averages of all the states. Each state has its own population, which varies the amount of energy usage. Because of this, the points are more scattered instead of being correlated into a curve.